So far, we've talked about the conservation of mass with this equation. So this side explains how the mass is changing inside a control volume with time. We then have a mass flow rate in minus a mass flow rate out. We have also, over time, explored the summation symbols to explain that there could be many inputs and outputs. Up until now, we've assumed that a process is steady state, so this term has gone away. And the example so far has basically said, well, if I know this, calculate that, or if I know this, calculate this, that. So let's explore a situation where this doesn't go away, and we need to deal with essentially an ordinary differential equation where mass in a CV is a function of time and perhaps other parameters. Here's an example to help us learn the process, so to speak. Imagine you have a tank. So this is the example. And you're given a tank. And it looks like this. And it has flow coming in, and it has flow exiting. And so far, what you know from the problem is the following. M dot in, so M dot in equals 14 kilograms per second. M dot exit is a little more complicated. It's 15 times L. So you ask yourself, what is L? And L is the measured height of the liquid column. So I could correct that. So L as a function of time. And oh, by the way, that's our goal. So L as a function of time equals what? What else do you know about this problem? Well, you know this tank has a base, and the base area equals A equals 0.3 meters squared. The density of the liquid is 1,000 kilograms per meter cubed, basically H2O. And at time equals 0 seconds, L equals 0. So how do we attack this one? Well, what we're going to do is we're going to look at our governing equations up here, and we're going to work with it. We're going to define each of these terms in terms of what is given. So let's go down. Give me a little space. OneNote. dm cv dt can be transformed into dt of what? Well, it looks like we have a area and a length. That would normally give us a volume. A volume times a density will give us mass. So let me write it out like this. Density, area, L, which then can be equal to rho A dl dt. Once you have that point, or that part of this equation, let's go to mi. Mi is straightforward, simply 14. ME is 15L. Right away, I think a light bulb should be going on. It basically says we're going to look to create an ordinary differential equation of L as a function of T, and probably a few other parameters. How will we do this? What we're going to do is we're going to combine this. So the first step, just to be clear, to work from your governing equation and substitute. Substitute, and combine. At this stage, we'd have rho to rho A dl dt equals 14 minus 15L, which can then be transferred into a rho A dl dt plus 15L equals 14. At this stage, we pretty much are, well, let me go one more step. dl dt by this term plus 15 over rho A L equals 14 over rho A. That is a differential equation that will not result, when we solve that equation, we will not find a particular number, but rather a function, and that's the key thing to keep in mind between algebraic equations and differential equations. Differential equations reveal functions. Algebraic equations, which is primarily what we deal with in this class, reveal values or constants. So let's take a deeper look now. If you have sort of a flashback, so to days before thermo, we remember a couple ideas. One is the product rule. The next is an exponential rule. And then this idea of an integrating factor. If you want, pause the video and test yourself and see if you can write out the product rule or the exponential rule, or explain what an integrating factor is. Going forward, we do know this to be the case, that this is equal to v du dt plus u dv dt. We also know the exponential rule as dt of EU is essentially EU du dt. And in our case, from above, an integrating factor for this equation up here term. So in our case, tau, we'll call our integrating factor, is 15 over rho A. This integrating factor comes right out of ODAs. If it's not clear, certainly go back and review it. Now let's try to implement all these ideas to derive a value for L as a function of time. So, going forward, dt dl dt plus tau L equals 14 tau divided by 15. I think you can see that because the rho A was originally under the 14, so tau has 15 divided by rho A, so if you divide by 15 and multiply through by tau, you're back to the original form on the right hand side. Now let's explore this left hand side. It's a classic look from ODE. We know based on this format that we could approximate using the product rule and the exponential rule the following equation. We could say that E tau small t dl dt plus E tau t tau L would equal to E tau t 14 tau 15. Now what do we do? Well, we recognize from the product rule, we could call all of this simply the derivative of E tau t L. And this is just carried on. The point of this is just to show it in a condensed format. What do you think we're going to do now to get L? Well, obviously, we're going to integrate. So let's try that. We'll integrate from 0 to t of this function. Then it would be the integral of E tau t 0 t 14 tau 15 dt. And of course we can bring all this out. And we know that the integral of this is going to be simply just 1 over the tau. So let's carry this forward. Oop, almost forgot the dt here. The left-hand side cancels, and we basically pull this down directly. So you have E tau t L equals 14 tau over 15 times 1 over tau. This comes from the integration of this term. E tau t. Let's see. Solving now for L, we have 14 over 15 plus C E tau t. Now what are we going to do? Well, we've got to solve for this c. How are we going to do that? We're going to use the initial condition. So if L at time equals 0, then c must equal negative 14 over 15. Can you see that? Because tau raised to a 0 power is 1, so it would be c plus this has to equal 0, shown here. The only way to do that is if this c equals negative 14 over 15. The final step. L equals 14 over 15 minus 14 over 15 e negative tau t. We just brought it up with this negative. Pulling the 14, 15 over 15 out, we have a 1 minus e tau t. Raise the negative power. That the final answer for L as a function of time. Now, how would we predict, before I go further and explain other approaches, how would we expect this to behave? So I think it's a good idea to try to think about. And so let's mark this as time. I'm sorry. This says L, the height, and this is time. So at time equals 0, we know that we need a starting point. Now, because if you remember, this tank is filling as well as emptying simultaneously, and by the way, the emptying is increasing, or the rate of emptying or outlet flow is increasing with L. It's sort of a complex process here. So at time equals 0, looking up here, think about how it will behave. At time equals 0, the exponential term, that goes to 0, so this would be e to 0 is a 1. Great, it works. Because 1 minus 1 is 0, boom. Now, as time increases, the exponent becomes larger and larger negative. So it becomes a smaller and smaller value. So as time increases, the ability of this term to take away from this 1 value decreases with time. As a result, what happens is there is a rise for filling, but a gradual plateauing as this term goes to 0. Feel free to plot this. I'll also post the Excel spreadsheet showing the plot more precisely, as well as a technique called the finite difference technique. I hope this was instructive. So before I end this lecture or segment, let me just go through it quickly or just review it. Transient conservation of mass problems involve tackling this entire equation, where you're trying to solve for mass as a function of time. The key idea is to recognize how to put these terms into given terms from a problem, which is what we did here. The second step is to substitute and combine, and also we could say simplify. Remember to not say that differently. Remember to pull into the problem solution methods, ideas you've learned from previous classes, mathematics in particular. Once you have it in a reduced format, Apply those mathematical techniques, solve for L, and think about it physically to see if it truly makes sense. I hope this has been instructive and useful. Thank you.